Okay. So what we want to look at is this idea of redox reactions then are reduction and oxidation reactions. In other words, it's cases where something has been reduced and something has been oxidized. Quickly remind me which is which. We said, Leo says GR, right? Or oil rig if you like, which means that the thing that loses electrons is oxidized, and the things that gains electrons is reduced, right? And those always come in pairs, because if something is losing electrons, something is gaining them, right? So these come in pairs. So with that in mind, not every reaction is a redox reaction. Not every reaction involves the movement of electrons. There's other ways in which things react. Sometimes it's obvious. This is an ionic reaction. So it is clear right off the hop. But even still, let's look. In this case, what's the oxidation number of zinc? Well, it's an element all by itself. So what will its oxidation number be? 0. Okay. What's the oxidation number of zinc here?
0.
Is it? We're in a compound. What kind of compound is that? Ionic. In an ionic compound, it's just its charge. What's the charge of zinc in zinc sulfide? Positive 2. All right. So zinc's oxidation number, rather, went from...
Orlando.
Yep.
The ON that you wrote, like positive 2, is that for like the whole like zinc sulfide or?
No, it's for zinc in zinc
just
sulfide.
Zinc, like,
Yep.
that.
So zinc's oxidation number changes from 0 to positive 2. What does that tell us? Was it reduced or oxidized? Very good. Therefore, it was oxidized.
I have a question. For sulfur, it would, like the solid part would be 0. So would the
Well,
other side be?
yeah, let's look here. The oxidation number of sulfur on its own is 0, right? And then here, the oxidation number of sulfur is, again, just its charge. And what's the charge of sulfur in an ionic compound? Always negative 2.
So a compound can have 2 charges. Oh, it balances.
Yeah, and of course we know that the oxidation numbers have to balance out to the overall charge. And zinc being positive 2, sulfur being negative 2 balances out to 0. So there we go. So sulfur's oxidation number changes from 0 to negative 2. Therefore, sulfur was reduced. And that means this is a redox reaction. What about this one? This one, hydrogen is always +1 or -1, but only -1 if it's with a metal, right? Or, yeah, there's some rare cases. But here, hydrogen's not going to change, oxygen's not going to change. So what's the only thing that could be changing? Sulfur. So let's check it. Does that make sense? Hydrogen is +1 with very few exceptions, and now these are exceptional cases. Oxygen is -2 with very few exceptions, and now these are exceptional changes. So the thing that could potentially change here would be sulfur. that make sense? So let's check if sulfur. What is the oxidation number of sulfur here? The oxidation number of sulfur in this case is, well, each oxygen is -3, right? Or -2 rather, and there's 3 of them for a total of -6. The whole thing has a charge of 0. So the thing has to add to 0. So if the oxygens are giving us -6, then sulfur must be good. How's that feel? Is that okay? So in this case, the oxidation number of sulfur is +6. And the way we got there is that this is 3 times -2 gives us -6, right? And these two sum to 0. Does that feel okay? Okay, what about over here? The 4 times -2 would give us -8. What about the hydrogens? 2 times +1 would give us +2. The whole thing has to sum to 0. So what's sulfur giving us here? The oxygen number of sulfur is +6. Speaking. Mm-hmm.
I thought you said the ON number should just be the charge.
This is not an ionic compound, right?
Oh.
So nothing has a charge.
So is it like a rule?
Right, that's a non-metal and a non-metal, grade 10 chemistry, right? So 2 non-metals make not an ionic compound, but covalent compound. Yeah, so there's no charge there. But that's the mistake you're going to want to make, right? You're going to be like, oh, sulfur's -2. But sulfur's only -2 if it's in an ionic compound. But here it's in a covalent compound. But again, that is the thing to look out for.
So it'll always equal 0 in covalent compounds?
Well, it doesn't equal 0 here. It's 6 here. They sum to 0. It always sums to the charge of whatever the thing is. In this case, what's the charge of SO3? 0. So these have to sum to 0. Whereas if we were looking at just SO4 -1 by itself, or -2 by itself, then the charges would have to sum to, or the oxidation numbers would have to sum to -2 because they sum to the charge. Did that answer your question? It's a good question. Yeah.
So is it just a rule that the products of whatever charge it is, it'll be the same charge at if the reactants has, like for example, in this it was like +6, is it a rule that the product would be the same charge as the...
Not necessarily, but the fact that it is tells us that the oxidation number hasn't changed.
Okay.
And if the oxidation number hasn't changed, then this is not a redox reaction. Does that make sense? So I just wanted to show you an example. Not every reaction involves changing electrical potential, changing redox potential. So this, since nothing, by which we mean oxygen, hydrogen, or sulfur, changes oxidation numbers, this is not a redox reaction. Nope. Here it is -2. Here it is -2. And here it is -2. We have different numbers of them put together, but each individual oxygen is -2 throughout. That was a good question too, but does that make sense? Whenever you're talking about oxidation numbers, you're talking about individual atoms involved in the reaction, not things overall. Because in the end, chemistry does happen between the orbitals of individual atoms, right? So here, when we're looking at oxidation numbers, we're not talking about whole compounds. We're talking about within each compound, each individual atom. Does that make sense? So again, nothing specific here. Now, you can always know every ionic reaction. Is that true? Am I about to make a sweeping untrue statement? No. Well, you don't want to be confident if you're wrong. That's terrible advice. Right? You want to, I would say, rather than be confident, be circumspect. But not too circumspect. Be circumspection?
No clue.
Well, it means to sort of think your way around things before you... Anyway, you want to be thoughtful. You want to be mindful before one makes... No, that's not dumb. That's just a different word. Circumspection actually usually has a negative implication. We actually mostly use it to mean somebody who sort of like talks their way around things sort of to a ridiculous point.
Bullshit, okay. You like that?
No, different.
It's the same thing, isn't it?
No, but they can be related. Bullshit isn't so much talking around something as it's just talking. It's just talking. Bullshit's a very specific thing, isn't it? Like, because if somebody like, it's different than just being wrong.
Yeah.
Right? You can be wrong without being like it's a certain brand of wrongness that like. In fact, you can even be right and still be bullshitting, wouldn't you say?
Yeah.
If you don't know that you're right, like if you're just kind of right.
I think it's that not knowledge.
Yeah, it's the not knowing what you're talking about that characterizes BS, I think. Anyway, I read a book once titled simply "On Bullshit." That was quite fascinating. It was sort of, but it made the argument that sort of our modern culture is the apotheosis sort of, proliferates. And I mean, whatever, that's always an easy book to write, right? Like, things today are terrible, but I don't know. Which I don't think. I think things today are...
Are you a pro-bullshitter now?
No. I am very much a believer, and I hope that I model this, God, I hope I do, that, like, epistemic humility is tremendously important.
What does epistemic mean?
Epistemology.
Oh.
How do we
I
spell
understand
this?
that.
Epistemology. How do we spell it? Somebody Google this for me. Epistemology. Epistemology is the study of how we know. It is the study of knowledge itself, right? So when we talk about epistemic humility, it means being humble about what you do and don't know, right? And trying to know the difference. Trying to get outside of that sort of, you've probably learned in some class or other about the Dunning-Kruger effect. The people who know the least about something tend to be the most confident in their knowledge about things. And that actually the more you know about something, the more humble you become about it because you're sort of aware of the limitations of your knowledge. So being epistemologically humble, I think, is really important. It's important to know what you don't know. And as somebody who doesn't know much, that's easy. But I don't know. Like... your mileage may vary. All right. Now, when we get to redox reactions, we're going to learn a new thing we have to balance. We have always had to balance how many carbons are on the left, how many carbons are on the right, how many hydrogens are on the left, how many hydrogens are on the right, how many oxygens are on the left, how many oxygens are on the right. But we're going to add a new element. How many electrons are moving on the right, and how many electrons are moving on the left. Does that make sense? That's a new thing we've never thought about before. The truth is, it's actually been hiding in a bunch of the reactions you've been balancing your whole chemistry career, and we've always just taken for granted, right? So this reaction up here is a perfect example. You don't have to write this. But we said zinc, zinc plus sulfur yields zinc sulfide, right? Okay. There we go. There's a reaction. Well, the truth is that what actually happens in this reaction is that zinc, well, what's happening here? Is zinc giving electrons or taking them?
Giving.
Okay. It's giving away 2 electrons, right? Oh, so it's giving them away. So they're a product, right? So it ends up giving us zinc with a 2+ charge and 2 electrons to spare, right? Does that make sense? And then what's sulfur doing in this reaction? Well, sulfur is actually taking electrons. How many? 2 of them. To form what? Well, sulfur with a -2 charge, right? And then what we can really say is that zinc with a 2+ charge plus sulfur with a 2- charge, what am I doing here? Can give us zinc sulfide. Now, we've never bothered to write any of this stuff, right? We've always just made this jump here, and we're going to continue to just make that jump there. Though when we first teach it to you, we show you that this is what happens, right? We actually, remember, we used to draw it, right? We'd draw zinc, and we'd say, well, we'd never use zinc as an example, but we would use, say, beryllium as an example with its 2 electrons in the outer shell, right? And we'd draw sulfur with 1, 2, 3, 4, 5, 6 electrons, and we'd actually show the transfer. So when you first learn this, we actually did account for the electrons. And then very quickly we teach you, we don't want to be bothered with that. We don't want to draw this every time. And we, if you're like me, maybe you learn the crisscross method in another class, or I do my stupid little chart where I say, okay, zinc likes to give up 2 electrons. So 1 zinc would give 2 electrons away. 2 zincs would give 4 electrons away. 3 drinks would give 6 electrons away. And of course, sulfur wants to take 2 electrons, so 1, right? And all that jazz. And we quickly teach you to stop thinking about electrons, right? And just do it quicker. And that's good because we want you to just do it quickly. But the truth is, this is what's actually happening in the reaction. And if we wanted to sum these up, right? We would never bother doing this, but we see, well, the reason we don't have to bother is that cancels with that, right? And this cancels with that, right? And the electrons cancel too, right? But what if I didn't cancel the electrons? What if I wrote it with the electrons in there? We could really say that if we take zinc and we give it to sulfur, which is going to need 2 electrons, we can get zinc sulfide. But to do that, the zinc has to have given away 2 electrons. Now, we'd never write it that way. That's a stupid way to write it. But do you see how, it's mathematically in there? It is a part of the reaction. We've just always canceled it away. That may feel a little weird and a little esoteric, but the reason we could always just not deal with it here is because ionic reactions, by virtue of there being big dumb rocks, this always just takes care of itself. Does that make sense? We've always been able to ignore electrons because we did ionic reactions, and in ionic reactions, there's only one way for them to happen. As I've always said, ionic compounds with big dumb rocks, this sorts itself out. And then we got to organic reactions and covalent reactions that weren't redox reactions. Note this nice acid-base neutralization here. Or no, not even neutralization. Note just this acid-base reaction, right? In this case, water is going to act as a base, and it's going to give up H plus ions, right? And we get a whole thing. Regardless, here, we're now going to look at reactions that are redox reactions, but they're not big dumb rocks of ionic compounds. They're covalent redox reactions, which means it's going to be challenging to figure out how to balance the electrons, and we're going to need a way to do that. I'm actually going to teach you 2 ways, because there's 2 ways that sort of get used at the university level, and I want you to be familiar with both. So if your prof next year is, an oxidation number method person, then you can do the oxidation number. And tomorrow I'm going to teach you what we call the half reaction method, because some profs like that. They both really are doing the same thing. They're just 2 ways of tracking it out. Does that make sense? So we're going to do this together. And you're going to find that this can be a little tricky. But what we are tracking here is, in addition to balancing atoms, which still has to happen, we're going to balance electrons. However many electrons get lost also have to get gained. Does that make sense? And another way of saying that is the change in the oxidation numbers has to net to 0. So if a bunch of things have oxidation numbers that go up, well, a whole bunch of other things better have oxidation numbers that go down, such that overall there's no change in overall oxidation number. Does that make sense? That's just 2 ways of saying the same thing, which is the movement of electrons must be balanced. Now, the thing to know is that in the case of this here, that had to mean the transfer of electrons. With covalent, it may just mean shifts in polarity, but that still has to balance out. Does that make sense? Oxidation number changes have to balance out. So, can we give that a try? Yes. All right. So we're going to, and note, this note has been shamelessly adapted shamelessly being the key, from the Durham Board of Continuing Education SCH4U package, because it was a really good explanation. I liked it, so I stole it. Good artists borrow, great artists steal. You know who said that? I said that. So let's get to it, shall we? The increase in oxidation number for an atom or ion must equal the decrease in the oxidation number of another atom or ion. In more simple terms, the increase and subsequent decrease in oxidation numbers got to be the same. Let's try to illustrate this. Let's take a look. We're going to look at this reaction here. Now, this reaction is kind of ugly. Can we all agree on that? Which is if you take HNO3, which is what? Nitric acid, and react it with H3ASO3, you will get nitrous oxide as a gas, H3ASO4, that's arsenate, I'm assuming. So nitric acid and arsenic acid will react to give us nitrous oxide, per arsenate, arsenic acid, and water, liquid. This would be very tricky to balance, even if we didn't have to balance. Or could potentially be tricky to balance, even if we didn't have to think about oxidation numbers, but we do. So first, we're just going to verify that this is a redox reaction. And for now, we'll assume all H's are +1. All right? So the oxidation number of H we're going to treat as +1. And the oxidation number of oxygen we're going to treat as -2. All right? Because the only thing we'd look for is if we had H as the negative ion, if we had chromium hydride or something, then it would be negative. And if we had any real oddball oxygen things going on, but we don't here. So this is a safe assumption. You'll learn how to spot the cases when these aren't true. So what are the only two things we actually have to track? Not oxygen. Oxygen's -2. Arsenic. Yeah. Or astatine. Astatine. Right? Right? Yeah. AS? Having a moment. Yeah. But it's astatine, right? I know, but I was wrong. I'm allowed to be wrong. I think you're right. It is arsenic. Okay. Anyway, whatever. AS. Having a moment. Do I teach this for a living? Yes. But you know what? I think you're right. Anyway, let's take a look. So, sometimes it's helpful to kind of do a little table here. So we'll do left side, right side, and we'll just track the oxidation number of each of these. Let's look at nitrogen first. In the left side here, what do they have to sum to here? They have to sum to 0. What are the oxygens giving us? -6. What is the hydrogen giving us? +1. So what's nitrogen got to be? +5. Okay, good. Does that make sense? So that's on the left side. Then let's look on the right side. On the right side, what is oxygen giving us? -2. What does this have to sum to? It has to sum to 0. So what's nitrogen giving us? +2. Okay. So then, while we're at it, let's look at the delta, the change. What's the change from nitrogen? Did it go up or down? By how much? Went down by 3. Okay. So already, is this a redox reaction? It's got to be. It's got to be a redox reaction because nitrogen's oxidation number is changing from +5 to +2, which means that it's losing not necessarily fully, because again, these are covalent compounds, but it's losing polar influence over 3 electrons. It's gaining, right? Electrons. It's gaining influence over that. So is this oxidized or reduced? Reduced, which again, remember, means that it's gaining electrons. Again, that doesn't mean gaining whole electrons. It might mean gaining polar influence, right? We're talking about electronegative interference here, but that's okay. What's the other thing we had to look at? Nitrogen and arsenic. All right. Let's look at arsenic. Where's my blue? There it is. Okay. In this case, what is oxygen giving us? -6. What is hydrogen giving us? +3. What's this all have to sum to? Has to sum to 0. So what is the arsenic giving us? +3. Okay. And then on this side, what is oxygen giving us? -8. What is hydrogen giving us? +3. So what's the arsenic got to be giving us if this whole thing sums to 0? +5. So from +3 to +5, is that going up or down? By how much? 2. So this tells us two things. First of all, is this oxidized or reduced? Okay, so that's good. We have one thing being oxidized, one thing being reduced. That's good. That's appropriate. But is that balanced? So this tells us two things. One, this is a redox reaction. All right, there is a delta in oxidation number, all right? But the second thing it tells us is it is not what? It's not balanced. Can you see that? And again, it isn't that it's not balanced in terms of, because if you look here, let's count really quickly. How many nitrogens on the left? 1. How many nitrogens on the right? 1. How many arsenics on the left? 1. How many arsenics on the right? 1. So the nitrogens and arsenics are balanced in terms of how many of each. We could keep going. How many hydrogens over here? 1, 2, 3, 4. Okay. How many hydrogens over here? 1, 2, 3, 4, 5. So we can see the reaction isn't balanced anyway. But regardless, we can tell it's not balanced just in its electrons. Does that make sense? Now, we could just try to balance the numbers, but you see that's tricky here. We've got oxygen in 3 different places on the left, 2 different on the right, 2 different places in the left. This could be a tricky thing to balance. And we're actually going to find that when you have a redox reaction, if you balance the electrons out, the rest can sometimes take care of itself, which can actually be a useful way to approach it. Does that make sense? So determine the increase in oxidation number for the element that's oxidized and the decrease in oxidation number for the element that's reduced. So we can say we've already done it. The change in oxidation number for nitrogen is -3, and the change in oxidation number for arsenic is +2. Is that comfortable? Found that above? All right. Cool. Now, what ratio could we work with for that? Is there something we could multiply these by that would balance this out? Where do these meet? What is the lowest common multiple of 3 and 2 is 6, right? Therefore, 2 nitrogens gives us a change in oxidation number of -6. Does that make sense? And how many arsenics would we need? 3 arsenics would give us a change in oxidation number of +6. And that would be balanced changes in oxidation number. How's that feel? Does that kind of make sense? So now we can actually look at our original equation. And we can just say that instead of 1 nitrogen, how many do I need? 2. So I'm just going to throw a 2 in front there, and now we know that. And then what does that react with from the original equation? H3ASO3. But how many of those do I need? 3. And sorry, is that H3ASNO3?
Ryan Fisher, please return to class.
Like that, right? Did I get it right? And then what's that going to yield? Well, again, how many nitrogens do we need to have? 2. So we'll just balance that out. 2. And that was that NOs?
Yeah.
Great. And does that have a charge? No. And then we'll react, and then we get how many H3ASO4s are we going to have? 3 of them. And then what's the last thing? Water. Okay, now, this still isn't going to quite be balanced, but there's only one thing I can change here. What's the only thing I can change here? The water. Does that make sense? So balancing it then by inspection would actually be pretty quick. Really, let's just count hydrogens, right? So here we can say left side, right side, and let's look at hydrogen. How many hydrogens on the left side? 2 plus 3 times 3 is 9 for a total of 11. And how many on the right side? 3 times 3 is 9, and 2 more is 11. Okay, so in that case, looks like we're okay. What about oxygens? Let's check them. Here we have 6, and here we have for a total of? Okay, here's hoping we're good. Here we have 2. 3 times 4 is? 2 and 12 is? And 1 more is? 15. So in this case, how are we doing? We're good. Again, I don't have to worry about nitrogen or arsenic because that's what we balanced. You can count them if you want. So this one is good. Therefore, this reaction is balanced. But if it wasn't, the only thing that I would have changed would have been, hi.
Sorry, Hein, could you use a box of math cubes?
No, but I bet Calford could.
Calford?
Yeah.
Thank you.
But thank you. Love me some math cubes. I could use them for all sorts of fun things, but I couldn't really use them for teaching this semester. How's that feel? Is that okay? Feels all right? So, now the truth is, this probably is the only way to balance this anyway, but when you're doing a redox reaction, a good thing to balance first is your electrons, or your oxidation numbers, which is one and the same thing, and everything else should work out around it. The only thing I might have had to change here is that water number. It's the only thing that didn't involve my redox species. Does that make sense? Okay, now, things can get a little trickier. Because of course they can. Which is a lot of redox reactions can only happen in the presence of something that can receive electrons or donate electrons. In other words, you may remember we did a reaction in our organic unit where we made esters. And what did we have to provide for it to make the reaction happen? Time, heat, and what was our catalyst? Sulfuric acid. And at the time we just said, you just need it. It's the conditions. But in this next step, we're actually going to learn why sometimes you need an acid to make a redox reaction happen. Because an esterification reaction, at the time we just learned it as a type of reaction, but it is a type of redox reaction. It involves the transfer of electrons. And so now we're going to see that sometimes you need things to be in acidic solution to make it happen. All right? So we're going to take, for example, and say this reaction here, which is you can take chlorate ions and react them with iodine gas dissolved in water, so aqueous iodine, to produce chlorine ions and the iodate ion. Right? So we can actually into the iodate. Now, is this balanced? No, it's not balanced. In fact, that's what we're doing here. We have to balance this reaction. Now, you're going to see here that this does not balance nicely. It balances very easily if all you want to do is, right? You could just throw 2 there, right? Because you've got 2 here, right? And then you'd have to put 2 there, and then you put 2 there, and you'll be fine. But you're going to see it's not that simple. And let's take a look at why it's not that simple. Can we? All right. So this reaction does happen, all right? If you take potassium chlorate and you mix it with iodine, you will actually get chlorine ions forming, and you'll get the iodate ion to form. All right? So you get a brand new thing. That, by the way, is an I, not an L. It occurs to me we're having a font issue here, so if you want to kind of make that a little clearer by going like that, that might help you out, because it kind of looks like CiO3, but it's not CiO3. That's ClO3, and that's Cl. You see what I'm saying? Okay, so first of all, we can always assume, unless I tell you otherwise, that the oxidation number of oxygen is -2, right? Which means, what are the oxidation numbers we're tracking here? Chlorine and iodine, right? And again, we're always looking at individual atoms, all right? So we're going to say, what is it on the left side? What is it on the right side? And how is it changing? And while we're at it, we could even say, is it oxidized or reduced, right? So let's look at chlorine. Here, what is the oxygen giving us? We have 3 of them. -6. What does this have to sum to? -1. So what must be the oxidation number of chlorine? +5. Good. Okay. What about on the right side? It's all by itself. And what does it have to sum to? -1. So its oxidation number is -1. What's that a change of? Is that going up or down? By how much? Down by 6. Is this being oxidized or reduced? Well, if the oxidation number is going down, it's being reduced, right? It's gaining electrons, right? It's getting more negative. Okay, so iodine better be being oxidized here. Let's find out. What's the oxidation number of iodine here? What's it sum to? 0. Okay, so that's easy. And then what about here? What's the oxygen giving us? -6. What's it have to sum to? -1. So what is the iodine giving you here then? +5. Okay. So what's the delta here? Going up or down? Up. By how much? 5. Oxidized or reduced? Oxidized. Yep. From 5 to -1? That's okay. Does that make sense? Yeah. Cool. All right. So what's the ratio here? This kind of sucks a little bit, right? What is, where does 6 and 5 meet? 30, right? Is there anything lower than 30? Because they don't meet at 15, they don't meet at, we gotta go to 30, right? That sucks. So the lowest common multiple of 6 and 5 is 30. Yuck. That means we need how many CLs? 5 CLs. And how many iodines? 6 of them, right? Because that'll take these both to 30. That will balance the oxidation numbers. So do you see how if all you did was take, don't write this, okay? Look at me. Don't write this. But if all you wanted to do was balance this thing, you could just do it with 2s, right? Do we see that? We could just say, oh yeah, I need 2 of those, 2 of those, and 2 of those, and everything balances, right? Except what doesn't balance? The change in electrons, the oxidation numbers. See? So we have no choice. We have to balance the oxidation numbers. Yeah.
Isn't the lowest common multiple normally just you flip them, so like in this case the chlorine?
Yeah, that's not always, that will always be a common multiple. It won't necessarily be the lowest common multiple, right? Like if you had, now I'm classic Joe moment having a moment. I'm Joe. Thank you. Like if you had 4 and 6, the lowest common multiple of those is 12. But if you just flip them, it'd be 24. So you'd be twice as big as you need to. Does that make sense? So just switching them will give you a common multiple, but it won't necessarily give you the lowest common multiple. Now, if you end up with a balanced chemical equation where everything could be divided by 2 at the end, it's not the end of the world. Just divide everything by 2. But do you see what I'm saying? Okay. So anyway, so what the reaction we have now would be is, go back and rewrite it. We said that we need 5 chlorines. So we'd say 5 Cl O3 minuses reacts with how many iodines? 6. Now be careful. 6 iodines. What number goes in front of here then? 3. Because this is not just I, this is I2. And what's that going to yield on the other side? How many Cl minuses?
6. 5.
Which one?
5.
Yep. And how many IO3s? 6 is correct. Good. And that has a negative charge. Okay. How's that feel? Okay, now, note, chlorine is balanced. Iodine is balanced. What is not balanced? Oxygen's not balanced. Does that mean that this reaction is impossible? No, because what is this reaction happening in? Water. Everything is aqueous, right? Everything is aqueous, which means what must be involved in this reaction?
Hydrogen.
Both, because water. So, you may notice that although the chlorine and iodine is balanced, the oxygen is not. Since this reaction occurs is aqueous, that's some quality writing here. That's what I get paid $100,000 a year to do, is string together a sentence that reads like that. I'm ashamed of myself. We can add water to balance the O atoms. In this case, let's look. How many oxygens do we have on this side? 15 oxygens, right? And what about over here? 6 times 3 is 18 oxygens. So we need 3 more oxygen atoms. So how would I do that? Well, we'll add water. We'll add water. And if we add water, how many of them do we need to add here? 3. So we can say 5 chlorate ions react with 3 iodine atoms and 3 waters to form 5 Cl minus ions and 6 IO3 minus ions. Now, oxygen is balanced. Are we done? No. But that's okay because we are in acidic solution here. This reaction, we're going to find actually, makes the reaction a little bit more acidic. Because how are we going to balance the hydrogens out?
Adding hydrogen ions.
H plus ions. And where will they go? Yeah. So how many hydrogens do we have over here altogether? 6 hydrogen ions. How many do we have over here? No hydrogen ions. So we need 6 more hydrogen atoms. Doesn't matter. And so we can do that, and we get 5 ClO3 ions can react with 3 iodine gas, or aqueous, like dissolved iodine, and 3 water to give us 5 chlorine ions, 6 IO3 ions, and 6 H plus ions. And this should be balanced. This is balanced for Cl, I, O, H, oxidation number, right? Which is important. Remember, we balance that. Nothing here should change that, because in water, the oxidation number of hydrogen is +1, and over here, the oxidation number of hydrogen is +1, right? So it's balanced for chlorine, iodine, oxygen, hydrogen, and oxidation number. And really quickly, it should also be balanced for charge. Because if you started off with a positive charge, you have to end off with a positive charge. If you start with a negative charge, you have to end with a negative charge. What is the overall charge here? Well, let's take a look. What's the charge on this side altogether? Nope, because how many of those do we have? Okay, so we have a -5 charge overall on the left side, right? In fact, I'm going to balance this down here. Let's just check charge. Left side, it is -5. And what about on the right? -5. What about on the right side? Here we have -5. What do we have here? Nope. -6 for a total of -11. And then we have +6, which brings us to -5. So the charge is also balanced. So everything that could be balanced is balanced. Does that make sense? Now, again, we've never thought about oxidation number and charge before we've thought about charge when balancing. We've never thought about oxidation number. That's new. But they should all be balanced. All the atoms need to be balanced. How the electrons move needs to be balanced. And if you do all that, the charge should also be balanced. So it doesn't hurt to check it. Now, that means that this reaction, this particular one, makes a solution more acidic. If you mix these things together in water, it's going to release H plus ions, and releasing H plus ions will make this reaction more acidic. That won't always be the case. Sometimes you won't end up adding H pluses to the right side. Sometimes you'll end up adding them to the left side. In those cases, you would need an acid present to begin with for the reaction to happen, because it would have to use up H plus ions. Does that make sense? This reaction wouldn't require an acidic solution to begin with, though it would actually acidify your solution. It would make the solution acidic. Does that make sense? But if the H plus ended up on the left side of this equation, which it often will, then that reaction can only happen if you have access to H plus ions. Now, there's always some H plus ions in water, but in neutral water, does anyone remember the concentration of H plus ions? Is that a hand? Remember, the Kw value of water is 1.0 times 10 to the negative 14, which means that the concentration of H plus ends up being 1.0 times 10 to the negative 7. The concentration of OH is 1.0 times 10 to the negative 7, giving us Kw of 1.0 times 10 to the negative 14. So in neutral water, there's almost no H plus, right? This reaction would increase that concentration of H plus dramatically, because this one produces H plus. But some reactions, the H plus will end up on the left. And in those, unless you add a strong acid, the reaction can't happen. That's why we had to add a strong acid to our esters lab. Okay, a little bit tricky, yeah? Can we try one more? Sometimes a reaction doesn't happen in an acidic solution. Sometimes it happens in a basic solution. In a basic solution, remind me, what do we have present? We have a high concentration of what in basic solution? No, what makes something basic? OH, very good. OH minus ions. So, let's take a look. We're going to do a different one here. If it's in basic solution, the only thing you have to keep in mind is that in a basic solution, there's tons of OH minus ions around. And if there's tons of OH minus ions around, what will they react with? Yeah, because don't forget, OH minus plus H plus will give you what? Will give you what? Very good. Very good. So let's take a look. Same thing. Is this a redox reaction? We don't need to worry about H. We're going to assume that H is always what? And we don't have to worry about O. We're going to assume it's always -2. So what do we have to track here? Yeah. Not magnesium, but manganese, right? But yeah, absolutely. Yes. So, first we'll look at carbon. What is carbon here? Well, what are the hydrogens giving us? And then another one, so positive 4. What's the oxygen giving us? And the whole thing has to come to 0, so what's carbon giving us? -2. All right, so carbon's -2 on the left. What's it here? This whole thing has to add to -2. What's the oxygen giving us? Here? -6, good. The whole thing has to add to -2, so what is the carbon giving us here? +4. So its oxidation number is going to change from -2 to +4. What's the delta there? Is it going up or down? By how much? Very good. You see that? From -2 to 4 is a change. It's going up. It's going up by 6. Is it being oxidized or reduced? Oxidized. Good. Okay. What about manganese? Manganese. What is oxygen giving us here? -8. What's this have to add to? -1. So what's manganese giving us? +7. Very good. Okay. And then what about over here? Yeah, very good. Because the oxygen's giving us -8 now, right? And the charge is -2. So this has to be giving us +6, right? So what's happening there? Okay, it's going down by how much? 1. Oxidized or reduced? Reduced. What's the ratio here? 6:1. So that's easy. We need to multiply all of the what? Yeah, so multiply manganese by 6 to balance, right? So that means that this reaction will become CH3OH plus 6 Mn. Oh my.
Forgot six.
Yes, I did. There we go. Okay. Now, our oxidation numbers are balanced. Does that make sense? But what is not balanced is, just like last time, oxygen. It's no problem. Let's count here. 6 times 4 is, and then we have one more here for a total of 25. All right. What about over here? 6 times 4 is 24, plus 3 more is 27. So we need 2 more. So 2 more oxygen, right? Which we're going to add in the form of water. Okay, so that's easy. We'll say CH3OH plus 6MnO4 minus plus 2 water will yield CO3 2 minus plus 6MnO4 2 minus. And we really could have done this in one step, but that's okay. Let's also add the H's we need. How many H's are we going to need?
4.
Well, let's count. How many H's do we have on this side now? 3, 4, 5, 6, 7, 8. So 8 hydrogens. What about over here? We have none. So what do we have to balance then on the other side? Plus 8 H pluses. Okay, good. But, and if this were in acidic solution, this is the answer. Does that make sense? But H plus OH minus yields water. Or another way of saying that is water can be H plus OH minus. In other words, they can go on the same side. So these H pluses, what are they going to bump into? OH minuses, right? Does that make sense? And what that means is that these H pluses will never actually be allowed to form. They will be in the middle, but actually those 8 H pluses at the end, 8 H pluses will actually be 8 waters. But that means we needed 8 OH minus ions to be available. Does that make sense? So what we can actually then say is that CH3OH plus 6MnO4 minus plus 2H2O, and then we can say, but we needed those 8 OH minus ions to be there. Does that make sense? They're going to be reactants. They had to be present to begin with. Will give us CO3 2 minus plus 6MnO4 2 minus plus 8 not H plus ions. But if we had those 8 OH minus ions to begin with, we'll actually get 8 waters. Does that make sense? So if you're in basic, again, in acidic solution, that would have been the answer. But in basic solution, it's not going to produce H plus and have those H pluses stick around. Does that make sense? Look at me. This can't be a product in basic solution because it will immediately find OH minus and react to form water. So the OH minus isn't one of our products. The OH minus is one of our reactants. It's going to get used up as this reaction happens so that these 8 H pluses actually become 8 H2Os. Good.
So is it just assumed that H pluses just automatically became water?
Yes.
Okay.
If you are in what kind of solution? Basic solution. If there's a lot... Now, I know there's always some OH minus in water, but if you were just in neutral water, there'd be practically no OH minus around. So this wouldn't happen to any meaningful extent. But in basic solution, there's lots of OH minus around, which means H pluses are not going to stick around. And now we're done, except what do you notice about this reaction that makes it a little awkward? It's balanced, it's correct, but there's something silly that we wouldn't leave there. There's water on both sides. So the last step would be to say, if we have 2 waters over here and then we say that makes 8 waters, then really we can just cancel that and say that this is 6. And so then the final reaction is that CH3OH, which now that we're doing the answer, I want to include my states of matter. So that would be aqueous methanol reacts with 6 permanganate ions and 8 OH minus ions from our basic solution to produce carbonate ions. Oh yeah, sorry, those are all aqueous. Thank you. I have the worst Q's on planet Earth. I'm ashamed of my Q's.
There has to be someone that's worse.
No, I don't accept it.
Your cues look like my cues. Does that mean my cues are bad?
Yes, terrible, the worst. Any other questions?
No.
Okay. And now we're balanced. Whew! How's that? A little bit nasty? A little bit nasty, right? But it takes practice. Again, if you're in basic solution, you just have to be aware that you can't have any H pluses floating around in your reactions. Because in basic solution, you know what's never going to be allowed to float around? H pluses. But that's okay. Remember, anywhere where you end up with H pluses, just replace them with water. But what has to go on the opposite side of the reaction? OH minus in equal number. Does that make sense? Now, in this particular case, the H pluses were in the products, which means we replace them with water and put OH minus as a reactant. It can go the other way around. Do you know what I mean? I didn't want to do 6 examples, so I just put the things where I put them in these examples, but keep in mind that there's no rule that the H plus has to be a product. The H plus could also be a reactant, in which case you switch these things around. This stuff's a little bit tricky, but it really is, look at me. Once you get it, they're all the same. Do you know what I mean? Follow the steps. Why are we doing this? We're doing this because we can only say a reaction is balanced if everything about it is balanced, including the oxidation shift, including how electrons change. Any questions about that? Because I'm here. I'm here for you. You know who I'm here for? You. That's who. You know who else I'm here for? You. And you. And you. Don't forget about you. And you know what? You. And you know who else? You. And you. Now all these people around here? Oh, and her. Here for her too. All the people who skipped today, they're dead to me. I don't care. They can do what they want. But you guys, I'm here for you. And if you're listening from home, you're not actually dead to me. I was saying that hyperbolically, and I don't actually mean it. And obviously I love you and care about you just as much. And I'm definitely not making your exam harder than everyone else's. I would never do that. And I didn't give them a bunch of answers to the exam that you didn't get here.
Oh, is that why they're not here? Because they don't feel
That's right. They just think, hey, we're just floating through. I don't need to worry about